discussion, I do want to encourage you to remember a few of the things we talked about on Friday. And I don't remember if we actually finished the disc in this class or not on Friday, but either way, I don't want to go back down that road. Moments of inertia are not easy to calculate for the uninitiated. I don't know whether you will have to derive one or not. So I posted the video that includes the full derivation of the disk so that you should review it. But outside of that, you should memorize a couple of these. And I want to talk about the two that you should definitely know because they come out a bunch. That is, a rod or a stick rotated about either one end or the middle. This problem isn't presented the way you think it's going to be presented. Generally, what we see is a problem that has maybe a rod fixed to rotate about one end, and gravity acting on it causes it to spin. Almost always striking some mass at rest. These are conservation of energy and conservation of angular momentum questions, where knowing the moment of inertia of the rod is the least of your concerns, but having to take 2 or 3 minutes to look it up or derive it can substantially affect your ability to finish the exam. So knowing the moment of inertia about its center and about its end is a very valuable experience. I also want to point out that if they put, say, a ball mounted to the end of it, composite objects are merely the sum of the individual moments of inertia. Composite objects are the sums of the individual moments of inertia. That shouldn't be a surprise. Moment of inertia is already a sum. But that means once you know the moment of inertia of the ball, all you need to do is use the parallel axis theorem. To change the axis of rotation to match the situation. So now, if you know the ball and you know the rod, you can create the moment of inertia of this arrangement. It could be that the ball gets stuck to the rod after it strikes it. It could be that they're already together and one gets released. There's no telling. But moments of inertia add together. They're not vectors. But the objects have to have a common axis of rotation. I'd write that down. That if you want to make a composite object, they need to have a common axis of rotation. Now, that tends to be the way we see problems that involve a stick or a rod or something like that. But anything that can roll, they can use those in the questions. And you have 4 different shapes of objects that can roll. There's a ring, which I'm just going to try and draw a ring as distinct from a disc by making sure you understand that the mass is on the outer edge. And then a disc. Ring is mr squared, but a disk is 1/2 mr squared. But these are distinct from a solid sphere and a hollow sphere. So solid sphere, hollow sphere. One of the big takeaways that might not be being made obvious by me and should be is that ultimately the only difference between any of these objects is the fraction. That's not accidental. Memorize the fractions. They tell you what you need to know. All of these objects are going to have a moment of inertia that's going to involve the radius or the length of the object. That's obvious. But the fraction is the only thing that actually differentiates them. Having a pragmatic understanding of why these are the way they are is helpful. Put them in order, of smallest moment of inertia to largest moment of inertia. In your head, you should be able to see that the solid sphere is the smallest and the ring is the largest. Now, without any math and without being able to see the numbers, in your mind, you should imagine which one has more of the mass located close to the center. The more the mass is located close to the center, the easier it is to turn. Remember, moment of inertia is about how difficult it is to turn the object. So if the mass is located close to the center, it will be an easier object to turn. It will turn more easily, take less torque to do so. The ring is the hardest object to turn. But the solid sphere has almost all of its mass located close to the center. That's why it's the easiest to turn. Notice that the hollow sphere is the next hardest object to turn. There's very little mass located near the center. And by center, I mean the center of the axis of rotation. So these aren't accidental. You put all four of these on a ramp, the solid sphere makes it to the bottom first. The ring will be last. The one that's hardest to turn makes it down there last, while the one that's easiest to turn rolls with more acceleration. Now, those are all demos that tend to be done in like first year physics. We'll do the demos this week. For all of you who've never seen them, they're not that exciting, but it is appropriate that you understand what the point of moment of inertia is. It is inertia. It is how difficult it is to get something to turn. So we're going to take a look at an example problem today. And as an example goes, this might be complex to some of you, but it's a problem we've already done. We're going to talk about dynamics questions today. We're going to talk about statics later in the week, but dynamics today and tomorrow. Dynamics questions are ones we've already worked on before. In general, the force part of dynamics is net force equals MA. Dynamics is about unbalanced forces and the fact that the system will accelerate due to an unbalanced force. Torque adds a certain measure of complication then. Newton's second law applies for objects that are going to be spun just as much as it applies to objects that are going to be moved. If there's an unbalanced torque, our object will have an angular acceleration. But how much it accelerates will depend on the moment of inertia. The moment of inertia determines how easy or difficult it is to accelerate an object. These are vectors, so the direction of the net torque determines the direction of the angular acceleration. Part of the reason why it's a little more difficult to deal with torque than it is to deal with force is individual torques have to be individually calculated. A force is something you can see. You might have to break it into components, but a force is in and of itself something that you add together. Torques have to be individually calculated. I have to look at each force that acts on the system and see how or if it applies a torque. So here's our situation, and it's one that we've kind of seen before. I say kind of because we've done the problem one way. Today we're going to have to do it a different way. All right, so here's our problem. I'm going to have two boxes that are connected to a pulley, like so. There we go. The first box has a mass of 10, and the second box has a mass of 5 kilograms. But our pulley has a radius r and a mass of 5 kilograms. And our pulley is a disc. So, does disc end with a C or a K? Do you know it's actually either? You look it up. I've looked it up before because I couldn't remember one day whether it was a C or a K, because a compact disc has C at the end. A DVD disc has a C at the end, but a Frisbee as a disc has a K at the end. I wondered why. Either is an acceptable spelling though. So, just so you know, if it looks funny to have a K there, it's okay. You can put a C. It'll be the same. All right. We've done this problem before. And when we did this problem, it wasn't particularly challenging. It did take some practice for you guys who are novices to figure out some of the things that we had to do. But in general, most of you became relatively proficient at being able to solve a problem of this nature. That was, of course, until we deal with the idea that the disk has inertia. Up until this point, we would have just assumed that the tension in the string was the same everywhere on either side of the disk. That's no longer true. And here's where you should probably put something big and bold in your notes, because it is substantially different. If the disk has inertia, it requires an unbalanced torque to accelerate. If the disk has inertia, it requires an unbalanced torque to accelerate. Which means that the string pulling down on this side and the string pulling down on this side pull down with uneven tensions. It's almost as if some of the tension gets used up in order to cause the disc to turn, which is exactly what's happening. So I will label T1 on one side. Hello, Narav. Forget that it's Tuesday? Sorry, dude. And T2 on the other. Now, this is going to add a complication to the problem. Now, I know that you guys can set up this problem. You've done it before. As a reminder, you need to choose a direction for positive. And so I'm going to choose rotating this way for the disk to be the positive direction, which means consider box 1. The 10 kilogram box. The 10 kilogram box is experiencing two forces. It's experiencing a downward force of weight of 100 newtons and an upward force of tension. I'm going to make downwards positive to be consistent with the direction of rotation I chose for the disk. The sum of these two will cause a system-wide acceleration produced by 10A. Net force equals MA. We've done this before. This isn't new. In fact, the 5 kilogram will have a similar structure. We've done this before. Net force equals MA for the 5 kilogram. Upwards will be considered positive for the 5 kilogram. And that upwards tension is what's going to cause it to accelerate. T2 minus 50 will equal 5A. And these two accelerations are going to be the same. That part hasn't changed. The string doesn't stretch. Now, here's where it becomes a little more challenging. First, there are forces acting on the pulley. I didn't draw a free body diagram for the boxes. We've seen that enough where I don't feel like I have to. But I am going to stop and consider that there's a free body diagram that does act on the pulley. There are 4 forces that act on the pulley. There's the downward force of tension 1, there's a downward force of tension 2, and there's also the weight of the pulley. There's also that spindle that holds it up. I'm going to put a normal force on it. Now those have to add up to equal 0. The pulley doesn't change location. So the net force on the pulley isn't particularly exciting. It doesn't add anything to the problem. But the net torque on the pulley isn't 0. The pulley accelerates. In this case, there are 2 torques that cause the pulley to accelerate. The biggest difference in dealing with the torque equation is that although we can say that the net torque on the pulley is going to equal 1/2 mr squared, the moment of inertia of the pulley, times alpha for the pulley. That's going to be true for the pulley. Now, I've not given the radius, and there's a purpose for that. But I have given the mass, so you could put in the 5 kilograms for the mass. Now, to figure this out, though, we do have to realize that there are 2 torques that act on the pulley. One from each of the ropes that hangs off the side. There is a torque arm of length R that applies to tension 1 pulling down. Now, just something to put in your notes. When dealing with pulleys, the forces always have to be tangent. If you try to cause these forces to occur at an angle, the rope will just change position until it comes off the pulley at a tangent, which means all pulley problems have an angle of 90 degrees for the torque. That does add a certain amount of, convenience. But I would consider writing that down. Let's look at the first torque. The first torque is positive. Use your right-hand rule to convince yourself that the first torque causes a positive rotation on the wheel. You can use a 3-finger rule if you want, but we have said that the direction that is positive is out of the board. So using my 3-finger rule, the first torque applies a positive torque to the wheel. I often think that common sense is enough. But if not, when you use your 3-finger rule, you point your finger to the left in this diagram, and then your middle finger has to be pointed downwards to line up with that tension. That makes your thumb point out of the board or out of the page. So it's a positive torque. The torque is pretty straightforward, though. It's just going to be R times T1. I could put times a sine of 90 degrees, but we know it's always going to be sine 90 for a situation like this. Now the second torque is negative. R is in the opposite direction. So if you point your pointer finger to the right and your middle finger down, you'll get your thumb pointed into the page. That's a negative torque. So I'll explicitly make this torque negative. Torque arm length is the same, R times T2 times the sine of 90 degrees. Questions to this point? This is all the new stuff, but we've done all of these things already before. We've just not put them all together. The last piece is to add these together and set them equal to I alpha. So I'm going to add them together. I'll have RT1 minus RT2 Now, it's at this point where I need you guys who are on autopilot to tune in. Just like before, Newton's second law generates a group of relationships, a custom set of equations that can be used to solve your formula or solve for a value. In this case, I could use these to solve for T1, T2, or the acceleration. Ultimately, that's all we're here to do. But there are 1, 2, 3, 4 unknowns in only 3 equations. So there must be another piece of information that we need if we want to actually have any chance of solving this. And it's not too hard, but we talked about this a little bit. The only way the pulley actually rotates is if the string does not slip as it pulls across the pulley, which means the linear acceleration of the boxes has to be equal to a proportion of the angular acceleration if the rope moves without slipping. You need that condition, but this is the condition for the rope not slipping. If you have every reason to believe that that's true, that gives you a fourth equation, a way to bring all of these things together. Now, I'm going to stop here. Was T2 minus 50 equals 5A. The pulley experienced 2 torques, RT1 minus RT2, and that equaled 1/2 times 5 R squared times alpha. And the conditions for not slipping are A equals R alpha. Those are the 4 things. We derived 3 of them. One of them, this, is the condition for not slipping. If you want to know how to do this, plug everything into the torque equation. For you guys who don't want to think too much, plug everything into the torque equation. That's how this is done. Use the torque equation as your center. Solve everything else that you can and plug into the torque equation. So you're going to solve for T1 here, plug it into the torque equation. You're going to solve for T2 here, plug it into the torque equation. You'll solve for alpha here and plug it into the torque equation. Now go. So if you're making this your center, which is what I'm really trying to encourage you to do, then each of these other ones you're eliminating a variable. This process is going to get us the acceleration. We're eliminating everything else. So T1, it equals 100 minus 10A. T2 equals 50 plus 5A. So we start substituting in. I'll get R times 100 minus 10A minus R times 50 plus 5A equals 1/2 times 5 times R squared times A over R. That's all the substitution. Any problems with that? Are you sure? Because that's not what I saw when I walked out there. And the next thing you should see is that all the R's cancel, which should be an odd thing to happen. So for those of you who don't know why that happens, I want you to think about the 2 things that we substituted in. First, the moment of inertia tells us that the bigger the object is, the harder it is to turn because the mass is more further away from the axis of rotation. But this tells us that with every turn, it moves faster if it's bigger. Well, those 2 things are... It should be clear that those 2 things are kind of counterpoints. That although it's harder to turn, you get more acceleration out of each turn. And that's why all of it cancels out, leaving you with a relatively simple Algebra 1 kind of response. Now, I have no patience to do this. That's for you guys to do. I believe the answer comes out to be about 2.9 meters per second squared. Now, I also want you to consider that solving for T1, T2, alpha, those are all fair game. Generally, getting the acceleration is the easiest of the things to get, generally. And also be aware, the normal force should be less than the weights of all the objects. That might not seem obvious as to why, but if you consider that the normal force has to pull all those boxes up, some of you think it should be lifting the weight of everything that's below it. But it's not. The system is accelerating downwards, so it doesn't have to lift with as much force as the weight of all the objects, because one of the objects is falling down towards the ground. Now, before I go on to the next arrangement, I want you to note that this is just one sample of what these problems look like. Obviously now, every problem that had a pulley here and a box hanging on either side, now the pulley can have mass, which changes all of those questions and adds a complication. It's solved exactly the way we just saw it. But that also means there's a whole group of problems we've never seen before, like I could have a box with just a pulley and a box. Right, this system doesn't accelerate at g because the pulley has inertia. So the string slowly unwinds because it's going to take energy to get that pulley to turn. If it was a massless pulley, the object would just fall. It doesn't work that way now. Or turn this around. Like a spool of ribbon. If you drop it, there's a torque here that causes this to rotate. It doesn't just fall at g, it rolls down the ribbon as it unrolls itself. These kinds of problems are very typical and ones we're going to have to take a look at. The yo-yo question is actually even harder because the yo-yo has an inner radius, but the object has an outer radius, so the moment of inertia is not directly related to the torque in the way that these other objects are. Not to mention, there's every reason to believe that you could have a problem where your pulley has multiple radii. Absolutely nothing wrong with these kinds of questions. All of these are the same question. Slight variations, but offer us the same question. Not to mention that none of these things have to be discs. They can be any other kind of shape they want to throw in there. A solid sphere, a hollow sphere, doesn't matter. There was a problem a couple of years ago where instead of this, they had a solid ball on a table. And that's what was connected over here to a pulley. Something like that. And it caused this thing to spin. So these are all Atwood machine questions. They all have the same types of dynamics we've seen before. They're all going to be net force and net torque equals ma or I alpha. They're all going to be solved the exact same way. Generally, plugging into the torque equation will be best. Now, I guarantee you it is not, help me, mother. It is not equal to mu s times the normal force. It will be much less than that. These two questions are what we're going to do tomorrow. But to make it easier for you, I would encourage you to come up with a free body diagram tonight. And consider the torques acting on the object. This is not an easy consideration, so please give it a few minutes of thought, 5-10 minutes tonight. All right.